Hi everyone, my name is Yi Zhang. I am a PhD candidate supervised by Professor Shakotai and Professor Heath at the University of Texas at Austin. Thanks for joining me today. The paper that I'm going to present is titled MmWave Codebook Selection in Rapidly Varying Channels via Multinomial Thompson Sampling. Here is the outline of this talk. I will first go through the introduction and the motivation of our work. Then I will talk about how we model the codebook selection problem as a multi-unbanded problem. Afterwards, I will show how Thompson sampling-based algorithms could be used to solve this codebook selection problem. Finally, this talk will end up with some experimental results with real-world mmWave measurement. Let's start with the introduction. It is well known that the directional beamforming is required in mmWave system to deal with the path loss at a high frequency band. However, it is not clear how narrow a beam should be such that the best system performance could be achieved. The directional beams in mmWave system could be arranged as multiple codebooks, and each codebook consists of the beams with the same resolution, namely the same beam width. When deciding which codebook to use, there is a trade-off between beam chaining efficiency and the link quality. As shown in this figure, the codebook of wide beams can cover the entire scanning area with a few beams, while its antenna gain is smaller due to the less directionality. In contrast, the codebook of narrow beam can establish a link with very high SNR, while the associated overhead is non-negligible. This is because the narrower beams can result in more beam scanning to cover the entire space. Moreover, the optimal codebook is also user or scenario dependent. For example, the wider beams are more beneficial to users that are close to the transmitter. This is because these users can tolerate very low beamforming gain due to their central location. In other words, they don't need to use narrow beams to marginally increase the link quality with a large overhead. While for the far away users, it would be the opposite choice. In practical mobile mmWave networks, the channel is rapidly varying, and there would be some unknown constraints or imperfection in the system. This makes the mmWave codebook selection problem very challenging. Some prior work has investigated this problem. The first thread focuses on offline database-driven methods. Unfortunately, this approach requires a large amount of data to build a reliable database. Further, there is very limited theoretical analysis of their performance. Besides that, some model-driven approaches solve the codebook optimization by relying on accurate channel and beam pattern models, etc. Another line of related work is the beam alignment design, which is widely studied in past years. It focuses on selecting the best beam from a single codebook, and it usually does not consider the beam width effect and does not explore the beam chaining result over time. Therefore, no prior work has solved the mmWave codebook selection problem with online learning techniques. In the middle of a database-driven method and the model-driven approach, we aim at leveraging online learning techniques as it is suitable to deal with the fast varying channel. So given all this, the contribution of this paper is threefold. We first model the mmWave codebook selection as a multi-unbanded problem, such that we can solve it in an online learning manner. Further, we also explore some natural structure of the codebooks to speed up our learning process. The second contribution of this work is that we design several variations of Thompson sampling-based algorithms to solve the codebook selection problem. These algorithms are designed with or without the structure of codebooks. Moreover, based on some more recent theoretical work on Thompson sampling, we also justify the regret bound of our proposed algorithms. Finally, we evaluate the model, the assumption, and the proposed algorithms with the real-world mmWave measurements. Now let's look into our system modeling. We consider a mobile ad hoc network where a transmitter establishes the wireless link with the receiver by doing codebook-based bin scanning. There are multiple codebooks available at the transmitter, while the receiver only has one fixed codebook due to the hardware limitations. The codebooks are indexed from low resolution to high resolution, and the objective is to identify the optimal codebook that achieves the highest expected system throughput. We consider a slot-based system, and each communication time slot includes a bin alignment phase and a data transmission phase. At the bin alignment phase, the transmitter selects one of the available codebooks to perform the bin chaining with the receiver by testing all bins within this codebook. At the end of this phase, the index of the bin with the highest SNR will be sent back to the transmitter. Then the transmitter will use this best bin to transmit the data for the remaining time resources in this time slot. In particular, the transmitter will use the highest supportable modulation and coding scheme for data transmission. And we assume there is M+1 MCS levels, and MCS0 refers to a failed connection with the zero data rate. Therefore, given a codebook, the link quality is decided in terms of SNR, and the link data rate is further decided in terms of MCS levels. So this system under rapidly varying channel can be further summarized as the right-hand side. There's an unknown channel distribution F channel. Given a codebook, there would be an unknown receive SNR distribution FSNR. As a result, the MCS levels follow a multinomial distribution with M+1 categories. By knowing this category distribution, we know how good a codebook is. We now provide some more denotations to further characterize the performance of a codebook. We denote the PIK as the probability of using MCS level I when playing the kth codebook. Let the delta R denote the delta Rn denote the exact data rate associated with the MCS level M, and the Rm denote the normalized data rate of MCS level M. So without the loss of generality, higher MCS level, higher data rate. So given these denotations, the expected instantaneous data rate of using the kth codebook would be the inner product of the normalized rate vector and the probability vector. Note this instantaneous data rate of the link is calculated without considering the overhead. So to further consider the overhead, we define effective data rate. We recall that the low resolution costs less chaining time but result in a low MCS level, and a high resolution codebook costs a larger chaining time but generally provides a high MCS. Accordingly, we define an effective coefficient for each codebook, denoted by CK if it is defined as the ratio of the time allocated for data transmission phase over the total time slot, which is given as this expression. And it is worth pointing out that the time slot duration is fixed. As a result, the reward of a case codebook is finally defined as the expected effective data rate, which is the product of the known effective coefficient and the unknown instantaneous data rate. So under this multi-unbanded setting, the optimal codebook is the one that provides the largest expected data rate, and the cumulative regret is also defined here. And our objective is to minimize this cumulative regret, namely, we aim at minimizing the loss of learning the optimal codebook. After presenting the system model, we will introduce some natural structure among codebooks when we index the codebooks from low resolution to high resolution. The first assumption is that the instantaneous data rate is non-decreasing. This assumption is quite straightforward, since regardless of bin chaining overhead, the narrower bins usually provides a higher antenna gain. as shown in this example. The codebook of narrowbeams can make the probability mass function of MCS level more concentrated on high levels, and this helps to achieve a higher instantaneous data rate. The other assumption is that the effective data rates have a unimodal pattern. This assumption is motivated by the fact that the channel capacity of a link is actually a unimodal function with respect to beam width. This is shown by a prior work. Our assumption indeed further assumes that after taking the expectation over the channel edge, it is still a unimodal function with respect to beam width. In our later section about experimental results, we will show that these two assumptions are both validated with the real-world mini-midwave measurements. So I'm now going to present our designed Thompson sampling-based bandy algorithms to solve the model the codebook selection problem. In this paper, we designed 4 variations of Thompson sampling algorithms with or without the two assumptions in last slide. In this talk, we will focus on 2 of them. One case is without any assumptions, and the other one will take advantage of the assumption 3, that unimodal assumption. Let's warm up with Thompson sampling. Thompson sampling is a Bayesian type approach to estimate a distribution, and it is originally proposed by William Thompson in 1933, and then it was revisited for multi-unbanded in 1990s. The essential idea of Thompson sampling can be summarized as 4 steps here. Suppose X follows an unknown distribution F, which is parameterized by theta. We then set a prior distribution for this parameter theta. For each time we get an observation of X by sampling from the unknown distribution f theta, we update our prior of theta with this observation by the Bayesian rules. A toy example can be given here. Suppose X is a Bernoulli variable with a parameter 0.75, and the beta distribution would be the perfect prior distribution of theta, because beta is the conjugate prior for Bernoulli, and the posterior update would have a closed form expression. This prior is initialized by setting the parameter alpha and beta to 1, meaning a uniform distribution between 0 and 1, because at this moment we have no information about the X. Then if we observe 1, we add a weight to alpha, and when we observe 0, we add a weight to beta. The evolution of the probability density function of this updated prior is shown as an animation here. We can see that with more samples, the beta distribution gradually concentrates to the ground truth 0.75. This is the basic idea how Thompson sampling approximates a distribution. Initial application of Thompson sampling mainly focuses on Bernoulli bandy problems. For example, Bernoulli-Thompson sampling was introduced into wireless network for the rate selection problem. And more recently, in 2020, Ryu and his colleagues have extended Bernoulli-Thompson sampling to multinomial Thompson sampling, which is a perfect fit to our codebook selection problem. This is because the reward of our codebooks exactly follow multinomial distributions with n+1 categories. Moreover, Dirichlet distribution is available there, as it is the conjugate prior distribution for multinomial distribution. This provides us with the closed form expression for posterior distribution update. Accordingly, by using multinomial Thompson sampling, the prior update is quite easy, and our algorithms would be computational efficient. So in this slide, we summarize the Thompson sampling-based bandy algorithm for codebook selection without any assumption. The key takeaway in this slide is that we sample from the Dirichlet priors and play the arms with the largest empirical predictor rewards. The term weighted in the algorithm means that the reward is weighted by the effective coefficient due to the bin chaining overhead. We recall that there is a potential structure of codebook also, especially that the effective data rate could be unimodal. To leverage the unimodal rewards among arms, two prior works have proposed to add an empirical leader exploration mechanism. To explain this mechanism, we provide two important definitions here. They are empirical leader and the neighbor of an arm. The empirical leader is defined as the arm which has the maximum of empirical mean until the current time slot. And the neighbor of an arm is defined as its two adjacent arms. Similar to prior work on unimodal bandit, we start from weighted multinomial Thompson sampling, and we revise the arm choosing policy as below. The red equation here reflects the leader exploration. It means that with a frequency parameter gamma, the empirical leader is played without any hesitation. Otherwise, for the other case, the weighted multinomial Thompson sampling is used within the neighbors of the empirical leader to explore the other arms. We can see that the unimodal bandit algorithm is more aggressive in exploring the best arm as much as possible. So in this slide, we show that the theoretical result of the proposed algorithms. Two key takeaways are highlighted here at the right-hand side. First of all, the unimodal multinomial Thompson sampling reduces the logarithmic regression from considering the suboptimal arms to only taking care of the neighbor of the optimal arm. So in our codebook's problem, it is reduced from k-1 to 2. Secondly, this is the first regret upper bound for unimodal Thompson sampling with multinomial arms. Our analysis is inspired by two recent works of multinomial Thompson sampling and the unimodal Bernoulli-Thompson sampling. In particular, so our regret upper bounds make a complement to the existing analysis of Thompson sampling. In this last section, we show how we evaluate our proposed algorithms with the real-world MmWave measurements. Here is the testbed that we used to collect the real-world MmWave channel measurements. It consists of two 12 antenna phase arrays working at 60 GHz. By activating different number of antennas, we can generate 6 codebooks of different beam width, as shown here. With these codebooks, we collect MmWave channel measurement in terms of SNR at different positions in our lab, as shown in this figure. As you can see, we take measurements following different predefined trajectories, and all the measurements are taken under line of sight condition. After data collection, we further did the interpolation for those channel measurements along the trajectories. And with the interpolated data, we can calculate the ground truth distribution of the MCS levels for each codebook. Finally, the generated distribution of MCS would be used in our simulation. We first validated our two assumptions with the collected channel measurement. In particular, we also add some synthetic random blockage loss to the real-world measurements to mimic some non-line of sight condition. From these two figures, we can see that the two assumptions hold under both non-line of sight and the line of sight conditions. Finally, the algorithm performance in terms of cumulative regret is shown in the left figure. We can see that the unimodal multinomial Thompson sampling outperforms the other bandit algorithms for our codebook selection problem. The convergence of the optimal arm is also shown in the right figure. We can see that the number of times that the optimal codebook, codebook 3, is played linearly increase with time. So to summarize this talk, In this paper, we model the MmWave Codebook selection problem under multi-unbanded setting. So this allows us to apply the online learning techniques to solve it. And particularly, each arm follows a multinomial distribution. We propose multiple variants of Thompson sampling-based bandit algorithms to solve our codebook selection problem, with or without exploiting the special structure among codebooks. We also provide upper regret bound for the proposed algorithms. In particular, the regret bound for the unimodal Thompson sampling with multinomial arms is a complement to the current analysis of Thompson sampling. Finally, we validate our model assumption and the proposed algorithms with the real-world MmWave measurements. Here is the key reference of this talk. Thank you for your listening, and I'm very happy to answer any question.